All right, let's talk about a star. It's way out there, about 7,200 light years from us in the constellation Ophiuchus. It's called Pulsar B1642-03. Now, you might think, okay, another star, what's the big deal? Well, this one is special. Turns out, it's been hiding not one, but two absolutely profound secrets about how our universe works. And today, we're going to decode them.
So first off, what is a pulsar? The simplest way to think about it is like a cosmic lighthouse. You've got this super dense collapsed star, a neutron star, and it's spinning like crazy. As it whips around, it shoots out beams of radiation from its poles. And if one of those beams happens to sweep past us here on Earth, we see a little pulse of light. Blink, 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 a celestial beacon.
And when I say spinning like crazy, I am not kidding. Our star, B1642-03, completes a full rotation in just 0.388 seconds. That is unbelievably fast. It spins more than twice in the time it takes you to snap your fingers. This kind of precision makes pulsars some of the best clocks in the entire universe. Or so we thought.
Now, this pulsar isn't just some random dot in the sky. It's actually a landmark. You see, it's one of the 14 pulsars that Carl Sagan and his team used to create a map on the golden records aboard the Pioneer and Voyager spacecraft. It's literally part of our message in a bottle to the cosmos, designed to tell any intelligent life out there how to find us. So yeah, figuring this star out is kind of a big deal.
Okay, so that brings us to our first puzzle. For decades, the radio signal we got from this pulsar was a mess. It wasn't the clean, predictable pulse you'd expect from a cosmic lighthouse. Instead, the light was chaotic, jumbled, and just plain disordered. And scientists had to ask, why?
To understand the problem, you gotta know that scientists basically group pulsars by how organized their light is. You have your R1 pulsars, which are neat and tidy, very predictable. Then you have R3s, with two clear signals on top of each other. And then there's the R2 category. These are the problem children. Their signals are messy, complex, and super jumbled. And yep, that's exactly where our star belongs.
So the big question was, what was going on here? Was this pulsar just fundamentally different from the others? Was it operating under some other set of physical rules we didn't know about? Or was there something else going on? A hidden pattern, maybe, buried deep inside all that noise? This was the first great puzzle of B1642-3.
The answer, as it turns out, was brilliant. It came not from looking harder at the data, but by looking at less of it. A team of researchers had this wild idea. What if the real signal was just being drowned out by its own static?
So here's what they did, and it's so elegantly simple. They took all that messy data from the pulsar, and they basically threw out 97% of it. Yep, you heard that right. They just ignored all the jumbled, chaotic parts. They decided to focus only on the tiny 3% of the signal that was almost perfectly organized, or what they call highly polarized. It was a massive gamble, but boy did it pay off.
Because once they stripped all that noise away, what was left behind wasn't random at all. It was this perfect, elegant, S-shaped curve. And this S-curve is the classic signature that had been predicted for decades by the leading theory of how pulsar radio beams work. The beautiful, clean signal was there the whole time, just buried under all that chaos.
Now, finding this was a huge deal. It provided some of the strongest evidence we've ever had that a theory called coherent curvature radiation is how all pulsars shine. It proved that our models of physics hold up even in these incredibly extreme places. So even the messiest, most chaotic-looking pulsars out there are playing by the same fundamental rules. The first secret was out. There's order in the chaos. But just as one mystery was solved, another, even deeper one was still hanging around. This second puzzle had nothing to do with the light coming from the pulsar. No, this one was all about its timing. Because for a supposedly perfect cosmic clock, this thing had a really weird stutter. And this wasn't a quick find. This was a slow burn detective story that played out over 4 decades. Astronomers started timing this pulsar with insane precision all the way back in 1969. And as the years and decades rolled by, they started to notice something odd. The pulsar's perfect rhythm wasn't so perfect after all.
Every so often, the star would experience these things called glitches, tiny, sudden speed-ups in its spin. But on our star, these glitches seemed totally random. They'd happen at weird intervals, they'd be different sizes. For decades, it just looked like the chaotic ticking of a broken clock. But just like with the messy light signal, astronomers had a hunch that there might be a hidden pattern here, too. And after 40 years of meticulously collecting data, they finally had enough information to see the bigger picture. And what they found was incredible.
The big breakthrough came from a researcher named Shabanova. She and her team discovered that the glitches weren't random at all. In fact, there was a direct, linear relationship. The bigger the glitch, meaning the more the pulsar suddenly sped up, the longer you had to wait until the next one.
And you can see it right here in the data. It's so clear. A small glitch, like number 1 here, is followed by a shorter wait, about 886 days. But a much bigger glitch, like number 4, leads to a much, much longer wait, over 2,500 days. It's a perfect cause and effect system. Those seemingly random stutters were actually part of a predictable, interconnected dance.
So what does this all mean? It means the glitches are part of a massive overarching rhythm. Researchers figured out the whole pattern is being controlled by a colossal 60-year cycle. This completely changes how we think about neutron stars. They're not just simple spinning tops, they have complex engines deep inside with some kind of long-term memory. A clockwork mechanism is ticking away, governing everything. The illusion of randomness was shattered again.
So there you have it. One single star, watched for decades, gave up 2 incredible secrets. And each time it was the same story, finding a deep, profound sense of order hiding inside what looked like total chaos. So let's recap. Secret number 1 was in its light. By throwing out the noise, scientists proved that this messy pulsar shines just like all the others, confirming a universal theory of physics. Secret number 2 was in its spin. By tracking its timing for 40 years, they found its so-called random glitches were actually governed by a predictable 60-year cycle, revealing the clockwork heart of a star. And that leaves us with a pretty awe-inspiring thought, doesn't it? This whole story of discovery came from just one star, 7,200 light-years away. A star that we ourselves chose as a signpost for humanity's place in the cosmos. So if this much incredible hidden order can be found in just one point of light, imagine what other secrets are still out there, buried in the noise of millions of other stars, just waiting for us to figure out how to listen.